But if you think about this, if it's giving off this field, if it's giving off something, pheromones or whatever it happens to be outwards, if it gives it off in pulses, well, as that pulse gets farther and farther away, basically the strength of that field lessens because it's getting spread out over a larger and larger area. So it would make some sense that the force has to be somehow related to, well, how far you are away.
Oh, okay. That makes
Because
sense.
if I'm giving off my gravitons, if I give off 1,000 gravitons, it's spread over a very small area here, but it's spread over a larger area. And so it has to be somehow related to the surface area, which is an r squared value. So over r squared.
That is, like, in my mind, if I was thinking of this conceptually, would this be kind of related to, like, creating ripples in water? In terms of, like, a larger mass makes larger ripples?
I guess.
Yes, and the height of those ripples gets smaller the farther out you go.
Okay.
That's a good way of thinking.
All right, so, but I've left a little space there. Because if we think about units of force,
Newtons.
mass,
Kilogram.
so that's a kilogram squared, and radius or distance.
Meters.
So Newton is not a kilogram squared per meter squared, and so, as a matter of fact, depending on what units you are, this number right here might change, but this is generally symbolized by a capital G, and this is known as the gravitational constant.
Oh.
Isn't there a number like 6.67 10 to the negative 11?
That's
Is that-
it.
Is that
In
accurate?
SI units, 6.67 times 10 to the negative 11. That would-
Kilograms per meter second? No. Kilograms.
I think that's the pound one, isn't it?
I don't know the units.
That's
I just
SI.
remember that number from somewhere.
Whatever the units are, that has to make this equation work. And so the units are, well, I want to get rid of meter squared, and I want to get rid of kilogram squared, and I want to be left with newtons, so it's Newton meter squared per kilogram squared.
I would have never.
Wait, so what's 9.91? Oh, that's my bad.
All right, so 2 points. One, it's not an exact number. It is found experimentally in what I sort of figure is the most tedious experiment that's ever been conducted in physics. Basically, the way you do it is you have a mass that is attached to some sort of wire, something that you know how much effort it takes to twist it. You bring another mass near it, and you look to see how this reacts to the other masses. Oops. That's what you call it. That is a three-dimensional drawing, just in case you're trying to figure out what I'm drawing there. Basically, I've got these two masses down here, and I can put them in a set position. I bring this other one down, attached to a wire, put them here, and it should twist based upon the attraction to these two masses here.
Oh.
How much it twists, I have to somehow figure out how much it twists. And when I do that, I can figure out how much force was applied, and then can do this right here, figure that number out. The trouble is, what we reason I call it probably one of the most tedious experiments ever done, is that it has to be completely encased. You can't have any breeze getting into it at all. It's incredibly a slow and very careful experiment because you're dealing with really tiny numbers here.
I was gonna ask, like, how do you prevent, I breathed through my nostril, or I moved my arm, which, like, created wind?
Yes, it is when I've seen pictures of it, it's enclosed in glass to help minimize. but it can't be completely enclosed in glass because you still need the thing to twist or
Yes.
turn. So
It's probably
I
for
just
fun.
picture it, going for a week to get your first number.
I mean, could they do this in space, in a vacuum, more vacuum-like setting and have it better results in theory?
All right, so if you're doing space, you-
Oh, well, then there's.
yeah, you
okay.
probably could, it probably would work. However, you still have to bring in some, yeah, it's.
No, I get why.
I'm just trying to think of all the little things that could mess it up, and the fact that you still are accelerating while you're going around there, there's still this force downwards. So if the masses, if these two masses aren't exact, that there's gonna be some off balance there.
Oh, that's why is that why you say that number is not exact? It's just
The number's not exact just because it's found experimentally. There's more digits after that, those are just the ones I remember. And you can look up the particle data group is a group that collects sort of the current numbers, and so you can look up to see how far they've gotten at this point.
Like that's all they do?
That, it's an international organization which basically, when you find some more precise value for something,
Oh, it goes.
it tracks it.
Okay, that's pretty cool.
So, when I was there, it was still in paperback, the book, which basically had all the information in it, was about that thick, and really thin pages, and my work for my PhD would have changed from one number, two numbers in it.
What? Not just two numbers, like
Yeah.
that.
And then that would have been beaten out by whoever did the next experiment. Because as you go, you get more and more data,
Yeah,
and so the more data, the better.
the more accurate the number becomes. Okay, that makes sense. That's pretty cool.
So at this point, since it's been 20 years, any vestige of whatever I had in there, gone.
Dang.
Do you know what's gone?
Pardon?
Do you know what's gone?
No, I don't know it's gone, but it should be gone.
Should be gone.
Somebody should have done the same analysis with more data.
20 years. Was a doctor at first? I'm planning on getting one.
What's the question?
Well, do you think you going to school for your doctorate was worth it?
Going for my doctorate was good for me.
Yeah. Like
But-
you feel like a better person after
Sometimes a more arrogant person.
I don't know if that's a good thing. You make everyone call you doctor?
I don't make people call me doctor.
No.
That's why I signed my things George/Dr. Fox, you know.
Just not Mr., right?
Just not Mr.
What about professor? Is that?
Yeah, officially, that's not my title, but officially my title is instructor.
I think doctor's cooler.
Doctor is cooler.
Where was it going with it? Oh, that's right, back over here. Is there any question out there which I might have potentially just ignored?
I am a little confused why you put I'm guessing that's newtons equals newtons meters squared over kilogram squared.
Times kilogram squared over meter squared. What I was getting towards is that the units of this have to be Newton meter squared per kilogram squared, so that
Okay.
this whole side over here becomes newtons.
Okay, so then whatever is left over is just newton equals newtons.
Yes.
Okay, thank you.
Which I believe is always a true
Yeah.
statement. All right, so let's do a quick plug and chug. If you have a calculator, please pull it out so that you can do this. I've had way too many students mess up with their calculators on this, so that's why I'm asking you to. You can do it, you can. Let's find the gravitational pull between me and my notebook right there. So gravitational constant, my mass is about, let's see, I gained some of it back, about 95 kilograms. Mass of that binder right there, we'll just say 2 kilograms. And the distance between us, 2.5 meters. So just a plug and chug.
Well, I thought R meant radius.
Well, if you think about that, say, for example, the Earth,
Yeah.
the gravitational pull on anything that's the same distance from the Earth would be the same, so it is sort of,
Oh, okay.
but R is the distance.
Okay. So it'd be, okay. That big number.
So I guess what we're actually not, we're not finding the force, we're finding the magnitude of the force.
Oh, sorry, we're not. You're multiplying it by the gravitational constant, right?
Yeah.
Okay, so, two. Is
You
this
got a number?
Is this a silent thing?
No,
Oh,
hoping
yeah.
everybody will do it, and if they
I
look
got
at the same
2
answer, we'll figure out why.
2.0368 times 10 to the negative 9.
That's what I got.
2.02768.
That's what I did, yeah, I think it's.
2.0, you're at 2.027
Yeah.
times
Six.
10 to the negative 9?
Yes.
Well, actually rounding would be 2.028.
And you had 2.03. Those are way too close to each other for it to be something, maybe just a slipped finger. Well, what if you do 6.7 instead of 6.67?
I did do 6.7, that was my mistake.
Okay. All right, so it's looking like this is the answer. If you're not getting this, you need to figure out why. You didn't get that?
To the negative 11?
Yes, 10 to the negative 11.
Okay. I don't know why I got it.
Are you off by?
It's kind of hard to see, so this is an old calculator.
Squared, 0.09. Oh, 95.
I got,
98.
Oh.
I got that.
Okay.
Yeah,
Thank you.
okay.
I got that.
Thanks.
That makes sense.
All right, anyone with a question right now, before we make it look harder?
Yeah.
All right, force is a vector, so let's bring in the vector piece of it. So the gravitational force on 1 from 2, similar to, oh wait, no, that's the other class, never mind. So when you're given the two subscripts like this is the force, the first one is the recipient, the second one is the source. So this is the force on mass 1 from mass 2.
Oh, okay. So if it were 2 from 1, it'd be force on mass 2 from 1.
If it were 2, 1, yes.
Okay.
Now,
Sorry.
I think most people's gut feeling is to reverse the numbers, to do source then target, but this is the traditional way of doing it, where you do target then source. Right, Pam?
Is that also what was done for, I think it was the relativity video? Is that the same
The
notation?
Galilean relativity?
Yes.
That is the motion of the first one with respect to the other one. So yeah, it's the same sense of the force on the first one with respect to the second
Okay,
one.
thank you.
All right, so we obviously, we have a vector on the left-hand side, we need something on the right-hand side. It's all done with respect to mass 2. So R2 hat. Have we talked about the radial unit vector? The R hat?
I don't think so.
Or not enough for enough memories there. When we're dealing with I hat, J hat, K hat, we decide the direction of those. R hat, we have slightly different rules. R hat's the radial unit vector. The decision we make with R hat is what is the center. It's radial, it's going out or it's going in. Well, actually, radial vector goes out. So the direction is away from the center. Oh, I left something off. Negative. supported.
Why is it negative?
Because if I have mass 1, mass 2, and I'm looking at the force acting on mass 1, it is being attracted to mass 2. Well, the radial unit vector for mass 2, the R2 hat, is a vector going away. R2 hat is going away from it, but this is in the opposite direction. The minus sign is saying it's in the opposite direction to the radial vector.
Okay.
And that's a unit?
It's a unit vector because I have the hat on it. I did have one of the math instructors say that in calculus, if you see the hat, that's just another vector symbol, it's not necessarily a unit vector. I do not recall that from my own calculus class, but been told that in calculus, that's not necessarily meaning unit, but in physics, it definitely does.
So we need to change at the top there, our value for the gravitational constant to negative 6.67.
Oh, the gravitational constant is still a positive number.
So why did you, can you explain why you changed it to negative then?
The negative here is associated with the direction.
Okay.
Just like if I have a displacement of -5 meters in the I hat direction, I would write displacement is -5 meters I hat. That's the magnitude right there, and the minus sign tells me it's opposite whatever I hat is.
Okay.
So the negative is saying opposite of the radial unit vector.
So it's going in,
Yes.
okay. The centret F, the rest word we don't say in terms of circular motion.
Oh. Well, in this case, it's not circular motion, it's more of a, I guess if you had to throw a circle into a circular force, that still seems odd. Yeah, I'm not comfortable with that. Never mind. However, let's bring in that motion. Let's bring in some circular motion. Let's figure out the mass of the Earth. Earth. Moon. The moon goes around the Earth. And anyone have any idea how long it takes for the moon to go around the Earth?
Like 365 and a quarter days or something like that.
That's how long it takes for them to go around the sun.
Oh, well.
Oh, 30. No, wait, there's 13 full moons.
29 days?
Somewhere around there.
28 days.
It's 28, 29, somewhere in there. We're gonna come up with a crude estimate. Let's go with 28 and a half, just to split the two. So the period, 28.5 days. And let's make it official and put the squiggles in there just to indicate that it's somewhere around there. And, oh, we need to know that distance.
10,000 miles.
We approximate, I'm gonna say 150,000.
Yeah.
150,000 miles.
Isn't it like 93,000 or something?
It's over for meters.
Oh.
Yeah, I'm not.
I'm new to the measuring and meters thing.
You got me.
As an American.
Oh, I was
And
way
it
off.
gives it to me in miles there.
Google's American too.
All right. 384,400 kilometers. Oh. I was not aware that it was even displayed there. Apparently that button only works sometimes. What number did I just say?
384,400.
That's kilometers. Kilo, 1,000. So 384,400,000 meters.
That's a long way.
384, yeah.
All right, so the Earth is going around, the moon's going around the Earth. Do the exact same process as we've been doing. It's simpler than the car on the banked curve, but force diagram of the moon. What are all the forces acting on the moon?
Gravity.
Gravity.
But how does,
Let's work on the wording.
oh.
Weight.
Weight.
I don't think weight really is appropriate.
Acceleration due to gravity.
Looking for a force.
Force
Force
of gravity.
due to
Yes, there we go. Force due to gravity. All right, so we got this
Force.
F sub G here, the direction indicated by the arrow. What else?
The Earth also, or are we just doing it for the moon?
Just all I care about is the moon right now.
Does it have that centripetal acceleration since it's going around it?
It will have centripetal acceleration, but that's not part of the force diagram. That's
Is-
coming in just a moment.
Is there an other force because the moon is moving?
No, we really don't care how the moon got
Okay.
moving to begin with. In terms of this is a problem you might care personally, and that might be your lifelong passion, but we are not discussing how the moon got started. It just got started somehow. All right, so there's the force diagram, just the force due to gravity.
Oh, that's it, that's it.
That was the 9.
How come there's not
Definitely no
other
tension.
force going the other, or you said we're just doing, never mind.
Yeah, there is a force pulling on the Earth. If you look at through the Kepler law derivations, the last video, we talk about the what's called the reduced mass, and that takes that into account.
Oh, dang.
But we're assuming that the Earth is still and the moon goes around us.
3 o'clock.
We have, and so however it got moving, the only force acting on it is this. What is the direction of acceleration?
Oh, to the.
To the center of the Earth.
Yes. It is centripetal motion. It's got, I have only one force. The acceleration better be in the same direction as that force. Unless you're calling Newton a liar.
That's all that.
I've seen that.
So, nothing to decompose, acceleration's in that direction. So why don't we make that the positive direction? And so now we are at the equation of motion, so F equals ma. My force is the gravitational force, is equal to mass times the centripetal acceleration.
Oh.
Substitution, we have a formula for this and this.